So, hello again. What we're going to talk about now is some examples of the application of the fundamental theorem of calculus for complex functions. And we're going to do things a couple of different ways, but I want to point out when it's possible and useful to actually use the fundamental theorem. So we're going to begin with an example we could do with parametrization, and in fact is set up as a parametric-like integral. And instead, we're going to try to do it with the fundamental theorem. So the exercise asks us to integrate the function z plus 3, which is analytic, along a path parametrized with the parametrization given here. So when you're looking at an integral like this, one of the first things to do is to imagine if you actually meet the conditions for applying the fundamental theorem of calculus. Because it would be very nice if we could evaluate this thing by plugging the beginning and end points of this curve into an antiderivative of z plus 3. So what sort of conditions do we need to meet? Well, z plus 3 had better have an analytic antiderivative, and that's easy to check because the antiderivative of z plus 3 is f of z is equal to 1/2 z squared plus 3z. So that's one of the antiderivatives. I just need one. This is analytic everywhere. And so certainly it's going to be analytic on a simply connected domain containing the curve. So if we're going to use the fundamental theorem of complex functions, then we're going to want to say that this integral is actually equal to f of b minus f of a, where the b and the a are the beginning and end point of the curve. So here's b, and here's a. Who knows what the curve does? If the fundamental theorem applies, we don't actually need to draw that. We need to know nothing about how the curve is parametrized or how it travels. We just need to know the endpoints. And so the only difficulty in this question is figuring out where this curve begins and ends. So if we know that x of t is equal to t, y of t is equal to 2t minus 1, and our values of t range between 0 and 1, then we can figure out our value of a by just plugging in t equals 0. So a is equal to x of 0 plus I y of 0, which is, let's see, 0 plus I times minus 1, so we get minus I. And b is equal to x of 1 plus I times y of 1, which is 1 plus I times 1. Right? So we apply the fundamental theorem of complex functions to this line integral, and that means that we can write that the integral over the curve of the function z plus 3 dz is equal to the antiderivative evaluated at 1 the antiderivative evaluated at 1 plus I minus the antiderivative evaluated at minus I. And so what is the antiderivative? It's 1/2 of z squared plus 3 times z minus 1/2 of z squared plus 3 times z. And yeah, so that's pretty straightforward. If we continue here, I think we end up with some algebra to do. I think this turns into something like 7/2 plus 7i. So this is just algebra to get from here to here. It's good practice for you to do that. Okay, but the idea is that getting away from having to deal with the parametrization and the chain rule makes this much easier to do, right? And one question that we might have is to think about in the future is, okay, so do we actually really need to check that this function is continuous and has an analytic antiderivative? Can't we just say something about the function itself being analytic, and does that force it to be the case that if the function is analytic, then it's guaranteed to have an analytic antiderivative. And that's a good question. In fact, we'll come back to that when we start talking about applications of what's called the Cauchy-Bourgeois theorem in the next chapter. Okay. So to continue our study of integration, we're going to look at the function f of z is equal to 1 over z minus a, which is sort of a crucially important function in complex analysis. And in the real case, it's pretty easy to integrate this, of course, because we know how to deal with this in the real case. If we ever have the function f of x is equal to 1 over x, then we can integrate that to get f of x is equal to the natural log of the absolute value of x plus c. It's all of the antiderivatives of f, with the idea here that the derivative of f, capital F of x, is little f of x. Right? So the antiderivative of 1 over x is the natural log of the absolute value of x. Now there's a condition here that we have to be wary of, right? That's not really going to carry over to the complex analysis, or that rather that we hide when we're doing this, which is that this function is not defined at x is equal to 0. And there's another problem, which is that when we integrate it, so this function, f of x is equal to 1 over x, is perfectly well defined and consistent for values of x that are positive and values of x that are negative, but the natural log cannot be applied to things that are negative, which is why we end up with the absolute value in the antiderivative. So we have to address the same set of questions in complex analysis. What do we do about the fact that this function has an asymptote? And how are we going to deal with the fact that the natural log itself is a multi-valued function? That is, the way we defined the natural log involved the argument. And so if the argument is involved, then something is going to be happening where I'm going to have to choose a branch of the logarithm. So I have to be really careful in the complex analysis setting when I'm integrating things like 1 over z minus a, which are going to integrate into logs, to deal with the fact that not only is there going to be an asymptote, but there's also going to be a branch cut where the definition of the function changes. And I have to be really careful about the contours that I consider when I do that. Okay, so the first thing we should think about is what sort of, what do we want to be true? So what do we want? Well, the extension theorem tells us that if the integral of 1 over x is the natural log of x, then it certainly should be the case that the integral of f should be something like log of z minus a, where this is the principal branch of the log. But I have to choose some definition of the logarithm. So maybe we'll choose the principal branch where we let the argument of z travel between minus pi. Let's say the argument of z minus a travel between minus pi and pi. Okay. And in fact, not even defined at pi here. So I could pick another branch of the log, and this would be equally well defined, but that's something we actively need to think about. And that actually is going to control where the contours that we integrate over are allowed to be. If I need it to be the case that the argument of z minus a is strictly between minus pi and pi, then I can't have a contour that goes through the line, the branch cut, the line where that function changes definition. So if we have the point z is equal to a right here, so say that that's the point z is equal to a, then of course I'm not allowed to have a contour that goes through that point when I'm integrating the function because it's not defined there. There's an asymptote. But further, this function is not only not defined at a, it changes definitions at all of these points. So this is the branch cut for f of, for log of z minus a. Because remember, as you come around this way, when you go through that line, now you've made the argument wrap and you're on a different branch of the logarithm. So the principal branch of the logarithm is restricted to angles between minus pi and pi, and if you slide through that line, then all of a sudden you're somewhere else, right? You're in a different piece of the logarithm. And so for the moment, we're going to not allow that to be, we're not going to do that. We're not going to allow a contour line to go through that branch cut. And this is generally one of the obstructions that takes place when we're talking about complex analysis. We have to be careful to know if we're dealing with a multi-valued function that we've defined one branch that we're going to be working with, and we're integrating, we have to make sure that the contour that we're integrating around doesn't actually pass through the branch cut. And a lot of the technique and sort of delicate nature of complex integration comes from working around the fact that this function has a pole at one point, and then a whole bunch of points I'm not allowed to pass a contour through, because not because the function is not defined there, but because I pass from one piece of the logarithm to a different piece, and so behavior is not going to be continuous. Okay. All right. So with that consideration taken care of, any other contour that we draw that does not pass through z equals a and does not pass through the branch cut, we just integrate like normal. After all, 1 over z minus a is an analytic function away from a, and the logarithm is analytic everywhere, away from its branch cut and away from its pole. So as an example of an admissible contour, you can imagine that we draw, say, I'll do it in green here. Suppose I have a point here, and I have a contour that travels around like this, and that's my contour C. Well, the logarithm is analytic in a neighborhood of that contour. What do I mean by a neighborhood? By a neighborhood, I imagine that I can draw sort of a little oval-shaped region around the outside of this. And that's an open, simply connected set. And that open, simply connected set U avoids z equals a and the branch cut. And what that means is that the logarithm of z minus a is analytic on u. And what that means is that we're actually allowed to use the fundamental theorem of calculus on this set, because we've stayed away from the places where f of z is equal to 1 over z minus a is either not defined or has a branch cut where I can't pass a contour through it. I can define an open set around that contour so that the logarithm is an analytic function, and that means that the fundamental theorem of calculus applies. So on a contour like this, and with a domain U that we've set up to evaluate the logarithm on, I'm allowed to use the fundamental theorem of complex functions. So in this setting, I'm allowed to write something like the integral over c of 1 over z minus a dz is equal to the log of z minus a evaluated from my initial point to my final point. Say this is the point z0, and this is the point z1. So this setup is going to allow us to act like we're back in the land of real calculus. Now, I don't have to have chosen the principal branch of the logarithm for my integral. I could choose any branch of the log I want. Later on, we'll see that I can change where the branch cut sits in order to deal with situations where maybe I do want to have contours that go over on that side. And we're going to talk about an example today where I work around the fact that there's a branch cut by integrating around a curve that does not touch the branch cut. Then we're going to take the limits as the ends come together to join that thing up into a closed loop. Okay, so these are all pieces of how the elegant nature of the fundamental theorem of complex functions can be used in situations that it doesn't really apply to with limiting arguments. Okay, now admittedly, there's a lot of technical stuff that happened here. Remember, the idea is that because in complex analysis we have multi-valued functions and we have to choose the branch where we're working, that when I set up a contour integral, I have to be aware of the existence of asymptotes, which is the same as in real calculus, but also where the branch cut is and making sure that my contours don't go through a branch cut if that's a place where a function changes definition. All right, so let's look at another example here. Okay, So real calculus techniques apply when using the fundamental theorem. And the reason is because the fundamental theorem of complex functions rests on the real fundamental theorem of calculus. And so that means that a lot of the anti-differentiation rules that we know from calculus apply here, and the techniques that we know as well. So, for example, integration by partial fractions works. So we can actually approach this integral in two different ways. The first thing is we can imagine, do we know an antiderivative of the function 1 over z squared plus 1? What if we were in real calculus? Because the extension theorem should allow us to say that if I know the antiderivative in real calculus, that same relationship should hold in complex analysis as well, because it extends off the real line. So in real calculus, this is something everybody should have buried in their heads forever. The integral of 1 over x squared plus 1 dx is equal to the arctangent of x. Of course, plus some arbitrary constant if we're doing with indefinite integrals. So the antiderivative of 1 over x squared plus 1 is arctangent of x plus c. So we can use this result in complex analysis, but we have to be slightly careful, because in real calculus, there's no value of x that I can put into x squared plus 1 that makes a 0 come out. 1 over x squared plus 1 is a function that's defined everywhere in the real line. So this holds on all of r. Okay? Holds everywhere. However, in complex analysis, there is a number that you can square and get -1 out and put a 0 in the denominator of this thing. So the function 1 over z squared plus 1 actually has an asymptote. At z is equal to I, because I squared plus 1 is equal to -1 plus 1, which is 0. So that anti-differentiation rule in the setting of complex analysis only works as long as we avoid the asymptote in the domain of the function, which exists at z is equal to I. So what that goes to say, when we actually look at the integral for this, that we're going to be allowed to use the fundamental theorem of calculus as long as the contour doesn't actually go through the point where the asymptote is located. The asymptote in this case being the point at I. So let's actually take a look at this particular example. We have a curve. I need to put another condition on this curve to address what I just talked about. So we have a contour that begins at a is equal to 0 and ends at b is equal to 1 plus I. When I wrote the question, I meant to say the straight line contour. So this is supposed to be straight line contour beginning at a is equal to 0 and ending at b is equal to 1 plus I. If we graph this, then we note that the bad spot in this curve is up here at z equals I, right? So if there was a bad spot on the domain of the function, there it is at z is equal to I. The contour that we're being asked to consider is the straight line contour that runs from 0 up to 1 plus I. Notice that that contour does not go through the asymptote, which again means that we could surround this with a neighborhood, is one way of thinking about it, which is sort of a simply connected open domain that the function is analytic on, because 1 over z squared plus 1 is analytic everywhere else. And that means the fundamental theorem of calculus applies here. And so it's the case that the integral over this particular contour of 1 over z squared plus 1 dz is the arctangent of z evaluated from 0 to 1 plus I, which is the arctangent of 1 plus I minus the arctangent of 0. Of course, the arctangent of 0 is just 0. On the real line, this function agrees with its real counterpart by the extension theorem. And so this is just the arctangent of 1 plus I. All right, so for our final example, we're going to deal with a more complicated idea here, which is we're going to go back to thinking about the log, but we're going to think about the logarithm or integrating 1 over z minus a, but now on a curve that's going to address, can we actually integrate on a closed loop that does run through the branch cut? And how do we do that? And so both the technique and the result of this example are going to point the way to one of the most important results in complex analysis, which is called Cauchy's integral theorem. All right, so we're going to try to go step by step here. Already looking at this, I think, all right, I'm integrating 1 over z minus a. So if I'm going to integrate 1 over z minus a, I have to be careful, because if capital F was equal to the logarithm of z, then f prime would be 1 over z. In fact, I can put a z minus a here and it won't change anything. And I've got to be a little bit careful because, again, this logarithm, this principal branch of the logarithm, is going to have an asymptote at a, and then a whole bunch of disallowed points along the branch cut where the logarithm changes definition, right? So if we're going to use the principal branch, which is standard, we have to be aware that we're not touching the asymptote and we're not having a contour that goes through the branch cut, because then the function with the antiderivative would change definitions, and we don't want that. So what we're going to do is we're going to look at a situation where we have a curve that looks like this. We're going to take a circle of radius r, and we're going to take an arc. And that arc is going to run around the asymptote like this. And we're going to let this arc of radius r be parametrized by its angle. And we're going to have a beginning angle and an ending angle. So the beginning angle here is going to be minus pi plus 1 over n. And the ending angle is going to be pi minus 1 over n. And that's going to be our contour C. So it's a circular arc that starts at the polar angle minus pi plus 1 over n and wraps all the way around until it gets to the other side of the branch cut. Everything okay? Everything here is okay. We've avoided the pole. We are not going through the branch cut. I'm still allowed to think, oh, okay, so there's an open domain around this, where the logarithm is analytic, the contour is inside of it, so I'm allowed to use the fundamental theorem of calculus. So the setup here is going to be okay. So we're going to parameterize this circular arc or semicircular arc with a standard parameterization, which looks like this. So this is the same sort of idea that you would have seen in Calculus 3 and in Calculus 4 if you took multivariable calculus, which is the A1 and the A2 sort of set the center of the circle. Those are the coordinates of the point A, real and imaginary parts. And then the r cosine t and the r sine t are going to be what gives us stretch out by a factor of r, and the cosine and sine wrap us in a circle around the arc. So this particular parameterization is going to start us at this point, and then we're going to travel around the curve like this until we end up at the ending point. And so that's kind of what we're going to do. We're going to integrate that function along this arc, and then we're going to see what happens when we take the limit as n goes to infinity. Because if you let n go to infinity, then those n's get closer and closer and closer to each other on opposite sides of the branch cut. And if... Okay, so we're ready to proceed. We know that we're going to be able to apply the fundamental theorem of calculus here because our contour is contained in the right sort of domain. But to use the fundamental theorem of calculus, I'm actually going to need to know the coordinates of the points at this point and at that point. And so it's worth taking the moment to actually calculate those. So we're going to use a couple of facts here. The first is we already know that A is equal to A1 plus IA2. And the second is, if you think about this for a second, this is equal to A1 plus IA2 plus r cosine t. In fact, we can even take out the r, plus r times cosine t plus I times the sine of t. And that, by Euler's identity, is a plus r e to the it. So this parameterization can be written much more simply as a plus r e to the it. So if we take our initial angle and our ending angle, then we can define the coordinates of the points at this point and that point as, well, my initial point is going to be this parameterization with this angle plugged in, which is a plus r e to the I minus pi, I was going to say minus pi over 2, minus pi plus 1 over n. And our final point, z1, that we get from plugging in this angle is going to be a plus r e to the I pi minus 1 over n. That gets us our initial and final points for the application of the fundamental theorem, where I plug them into the antiderivative. And now we're just ready to go. The integral over c of 1 over z minus a dz by the fundamental theorem of complex functions can be rewritten as the logarithm of z minus a evaluated from z naught, which was a plus r e to the I minus pi plus 1 over n, to a plus r e to the I pi minus 1 over n. Continuing our calculation, we're going to get the logarithm. Well, the a's are going to be subtracted, so we're going to get the logarithm of just r e to the I pi minus 1 over n minus the logarithm of r e to the I minus pi plus 1 over n. But by the definition of the logarithm, remember that log of z is equal to the natural log of the absolute value of z, or radius of z, plus I times the argument of z. So this becomes the natural log of r plus I times the argument of this number. But what is the argument of that number? It's this angle right here. So pi minus 1 over n. And then we subtract off, well, the logarithm of this number is going to be the natural log of its radius plus I times its argument, which is minus pi plus 1 over n. You subtract, and when the dust clears, what you end up with here is 2 pi I minus I 2 over n. The 2 pi I comes from this I pi and this negative I pi right here, negative I pi, which turns into a 2 pi I. And then we have a minus I 1 over n and another minus I 1 over n. So that's it. This is the value of that integral. So the integral over our particular contour of 1 over z minus a dz is equal to 2 pi I minus I 2 over n. Now, what I can do is I can take that curve, and you can imagine this is going to be a well-defined limit as I let this point and this point slide in towards the branch cut. So if I take a limit as n goes to infinity, what I'm going to end up with is the whole circle. These things are going to come together. So there's a. And yeah, the function is not defined at the branch cut, but we're not actually defining the function at the branch cut. What we're doing is we're just taking the limits of the integrals. So we're not taking the limit of the function and then integrating. We're integrating and then taking the limits. And so if I take this and I take the limit as n goes to infinity of the integral over c of 1 over z minus a dz, I end up with the limit as n goes to infinity of 2 pi I minus I 2 to the n, which is 2 pi I. And this result here is no accident. The fact that we ended up with 2 pi I when we've wrapped around an asymptote for a function is one of the sort of central ideas of all of the theory of complex integration. Okay, so we're going to be spending a lot more time on examples like this as we go forward, but the basic idea here is exactly what we've done. This sort of interplay between contours, limits, and the fundamental theorem of calculus, taking into consideration things like the fact that the logarithm has branch cuts that have to be dealt with, taking integrals of things that were not really well defined by taking integrals of well-defined things, and then taking limits. All of those techniques are going to be part of our study of complex integration as we go forward. And the subject of our next section is actually going to be the things that lead up to the Cauchy integral formula. So one thing to consider is you might think about what should happen when we have an integral over a closed curve of an analytic function. And that's not very hard to think about what should happen there if you think a little bit about what the fundamental theorem of calculus should apply, as long as several hypotheses are met in the functions analytic. All right, so I will see you guys next time to talk about the Cauchy-Goursat theorem, and we'll start heading towards the major theorems of complex integration. All right, take care.